Okay, for this module, we're going to talk about how we handle distributed loads. So sometimes, although we want to deal with vectors, the load we're encountering could be a load that's distributed over a certain distance. So we can picture this just to visualize. Perhaps it's a snow load. So maybe it has snowed and it's a certain height and it's distributed, in this case, over, say, 9 feet width. And what you'll see is the load is described as 50 pounds per foot. It'll always be in pounds per foot. And what it's telling you is that if I start at one end and move 1 foot over, then the weight of all the load above it is 50 pounds. So for every 1 foot that I travel along this length, the weight above is 50 pounds. So we have 50 pounds per foot, and we would like to get rid of this uniform load and replace it with a vector. So how do we do that? Well, what we can do is use a resultant force. And the resultant force is going to act right through the centroid, the center of the shape. In this case, we have a rectangle. So the center of that shape, since it's 9 feet total length, this centroid would just be half of that, or 4.5 feet. 4.5 feet from the left and 4.5 feet from the right. That's the location of the resultant. Now we would like to know what is the magnitude of that resultant force. And it's very actually straightforward. The resultant is just the area of the shape. So in this case we have a rectangle, and the area of a rectangle is base times height. So let's see, what is the base of this rectangle? It's 9 feet. So we put 9 feet in. What is the height of that rectangle? It's 50 pounds per foot. So we put in 50 pounds per foot. And if you do the math, you'll see that the feet on the denominator cancels with the feet on the numerator here. So 9 times 5 is 450, and the units are in pounds because it's a force, it's a vector. So that means that we can take that original drawing that we had of a uniform load and replace it with a single vector of 450 pounds, 4.5 feet from the left. So this can also be applied. What if we had a load like this? Maybe it was, for example, a snow load and the wind hit it, so it drifted to be higher on one side than the other side. We can use the same concept. This is a load that's distributed over 9 feet. The load, 50 pounds per foot, is the maximum. That's how much it is at this left end, 50 pounds per foot. Over here it goes to 0. So we do the same kind of thing. First of all, we say, where is the resultant located? And for any triangle, the centroid, instead of it being right in the middle like it was for a rectangle, it would be 1/3 of the total base dimension. So here's our total base dimension. We're always going to take that number and divide by 3, and that will tell us where the resultant of a triangle is. In this case, it's 3 feet. What about the magnitude? Well, it's just like before. It's the area of the shape. In this case, the shape is a triangle. So the area of a triangle is 1/2 base times height. So here's 1/2. Our base is 9 feet, so we plug in 9 feet. Our height is 50 pounds per foot, so we plug in 50 pounds per foot. You do the math, and you'll see that the answer is 225 pounds. Notice the units again. The feet on the denominator cancel with the feet on the numerator here. And that means we can replace that original distributed load, that original triangular load, with a single vector of 225 pounds located 3 feet from the left. Now we're going to be doing this an awful lot because in the real world almost all the loads are distributed loads. We mentioned snow loads, same thing for wind or earthquake, or even when you have a contact pressure between, let's say, for example, a truck and the road. There's contact pressure at the tire. So what we're going to do is simply take these rectangles and triangles and replace them with vectors, and then from then on we can go ahead and continue with their statics problem.